Hello, this is the next video in a playlist titled General Linear Models, Design of Experiments, and this is part 5 in a little mini series within that playlist that I'm calling One-Way Fixed Effects Anova. And here we're going to develop f-tests and confidence intervals for the parameters. So an f-test of no treatment effect is developed like this. And if you go back to the previous parts, the model we could consider without constraints and with constraints. And first, without constraints, the no treatment effect is that all the parameters, all the tau I parameters are equal to the same value, say their grand mean. This is for all I. And essentially that boils down to that our model looks like our y is equal to some constant plus error. And see part 4 for more details. Versus they're not all equal to a constant. So there is a treatment effect. Now with the constraint, and the constraint was that the sum of the taus is equal to 0, then the null hypothesis of no treatment effect is that all the tau i's are 0. And the alternative is at least one is not 0. And that's for some I. So the test statistic is this. We create an F distribution, or a test statistic with an F distribution. And for the distributional properties of these, I would refer you back to part 3 where we derive them. But the sum of squares treatment divided by sigma squared is a chi-squared with degrees of freedom a minus 1, and sum of squares error divided by sigma squared is a chi-squared with degrees of freedom an minus a. And so these are two chi-squareds divided by the degrees of freedom. But to be an f-test, the numerator and denominators have to be independent. And in part 4 we proved that these are indeed independent. Now this, the 1 over sigma squares cancel, and then sum of squares treatment divided by degrees of freedom is the mean square treatment, and sum squared error divided by its degrees of freedom is the mean square error. And in scalar notation it's this. And in part 3 we showed this. We looked at the expected value of this numerator and the expected value of this denominator. Now look, that on average the denominator is sigma squared. It's an unbiased estimate for the error variance. The numerator, under the null hypothesis, the expected value is sigma squared. So this is really close to 1. But under the null, or the alternative hypothesis, if it's true, then we expect it to be greater than sigma squared. So this numerator becomes much bigger than this, which then this is a bigger number, which drives it into the right tail of the F distribution. All these are summarized in what's called an Anova Table. So we have a source of our variation, which we have a total variation, the error variation, the treatment variation, and we look at those through the sum of squares. So we have sum of squares treatment, error, and total, the degrees of freedom associated with these. And most think the degrees of freedom have something to do with the number of independent parameters, that's a great rule of thumb, but it's really the rank of that quadratic matrix in quadratic form. The mean square error is you just take the sum of squares divided by the degrees of freedom, and then the F test statistic is the ratio of those two. And some will put a p-value out here too associated with this F test statistic. Now let's look at confidence intervals. Now confidence intervals, we need some sort of distributional property, and let's derive that. So y is equal to, not equal to, it's normally distributed with this mean. Now notice it's yij, so we're in the ith treatment arm, so that's why it's the ith treatment mean, and it has a variance of sigma squared. Notationally, we represent the treatment mean as yi dot, and the dot means we sum over that index. The expected value of this treatment mean is this, and then the expected value of this is mu plus tau I, but we're summing over j, so there's n of them, and the n's cancel, and we're just left with this overall treatment mean. The variance can be calculated like this. Now notice that when we calculate the variance of this constant has to come out squared. The variance of this is sigma squared. We're adding up sigma squared n times, so one of those cancels, and we're left with this. So the treatment mean is normally distributed with mu I and sigma squared over n as the variance. So then the test statistic becomes this. We take the variable minus the mean divided by the standard deviation, and that creates a standard normal distribution. And previously we've shown that the sum squares error divided by sigma squared is a chi-squared distribution with degrees of freedom, an minus a. That's, we have to take the square root. And then this is a t distribution if the numerator and denominator are independent. And then this, of course, simplifies to this. And this is to me, the magic formula that if you look at this numerator, and if we just replace an estimate of this sigma squared with MSE, with the mean squared error, that's what this is. So, that's just replace the sigma squared estimate, the sigma squared with an estimate, and it magically becomes a t distribution. But you have to be careful because the numerator and denominator degrees of freedom, or numerator and denominator have to be independent. So let's check to see if they're independent. Now up here, the only random variable is this yi dot bar. So we can represent that in matrix form like this. So this is the vector of treatment means, and we create an EI vector where it's a 1 in a component and zeros elsewhere, but that where it's where the 1 is, when you do this multiplication, it picks off the right mean, and then the treatment mean is my, where this is the perpendicular projection matrix on the column space of x. Sum of squared error is this, and then I have a video looking at the independence of quadratic forms, and we have to multiply the matrix here times this matrix, and if it's 0 then they're independent, but we instantly know that they are, because this is the perpendicular projection matrix on the column space of x, and this is the perpendicular projection matrix onto the orthogonal complement space of x. So in order for this to be satisfied, remember m shoves it down in the column space of x, but this lives in the orthogonal complement space of x. So there's only one vector that satisfies that, and that's the 0 vector. So they are independent. So then we can use that fact and create a confidence interval for the ith treatment mean, which is this. Right? So if we take that and divide it over, this is a t distribution, and then we add and subtract, the endpoints of the t. Anyway, so this is it. But what if we wanted to look at the difference between two treatment effects? Well, it can be shown that that's normally distributed with this mean and this variance. The test statistic, or the t statistic for this confidence interval, is we create a standard normal distribution, right? Take this random variable minus the mean divided by the standard deviation, and that creates a standard normal distribution. And this is a chi-squared divided by its degrees of freedom, square root, and we get this. But we have to check to see if they're independent, which we'll do in a second. This simplifies to this. Remember, just replace the sigma squared with an estimate, and it magically becomes a t distribution. I say that jokingly, of course. Now let's check to see if the numerator and denominator are independent. Now this is the only random variable, and this is. So I like to recreate this in matrix form. So we take the mean vector and then create a lambda which has a one component of 1 and another -1, and then the rest zeros. So when we do this product, it picks off the right means. And the treatment mean vector is my, and then we take this times that I minus m, which is 0, of course, from our previous page. So the confidence interval becomes, the difference of the means plus or minus the t statistic, square root of 2 times the mean squared error divided by n, and this is your confidence interval. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.